Okay. Well, I have a couple of review slides. So you guys did some problems that you handed in today to kind of apply this, right? No?
Oh, no.
That's due Monday. Okay, good, thanks. No, okay, sorry. No, you're fine. You will, if you choose to do the extra credit, right? This is what you'll be using. We talked about this yesterday. Huh, okay. We talked about this after we did the lab part. The fact that you get a whole bunch of tables of, we're not going to go over this again, but you get a bunch of tables of reduction values. Okay, you get a table for a bunch of this stuff, okay? And you want to try to make the potential of the cell positive. So, but you're going to have an oxidation part, remember? So like the lowest half cell reduction you're going to make actually oxidation. Okay, and you're going to come up with this. And this is also a repeat slide from yesterday. It's really being slow. Dun, dun, dun. Okay, so the next one is going to be Gibbs free energy is equal to negative N Faraday's constant times, there it is, times the cell potential. And this is a cool thing. Remember, it's a cool thing. It's a good relationship. But now this is under standard conditions. So this has to be, that little knot means that you're talking at 25 degrees Celsius, 1 molar concentration, 1 bar, 1 atmosphere pressure. Okay, so that's a review slide. Now we're on to a new slide. So the Nernst equation, which is also on your, I didn't bring mine today, I don't think, but on your equation sheet that you're going to have for your test, the Nernst equation looks at cell potential at non-standard conditions. So notice the E cell over here on the left, there's no knot there. It means it's non-standard conditions. Okay? So yes, you do have the Nernst equation or a form of it, right? It's the third one right there. That is a form of the Nernst equation we're going to get to. So non-standard temperature, non-standard pressure, although that's not in the equation, but non-standard temperature, you can see a T term there, okay? And the Q, I'm going to convince you of this, but the Q there, yeah, of course, that's your snapshot. That's your reaction quotient. And the Q will cover non-standard molar concentrations, okay? So this right here is non-standard molar concentrations. Big M for molar concentrations. Of course, this would be non-standard temperature. Non-standard temperature. See, I can't write with the stylus. Okay. So that's the Nernst equation. N is the same thing it's always been. N is the number of moles of electrons that are involved in your redox reaction. So let's just take out the T term. And actually, what you're going to have on your test, this is getting closer to what the equation sheet is on your test. It's close, but it doesn't entirely match up. If we take out the temperature term saying, all right, let's go with standard temperature, which is 25 Celsius, then actually that equation becomes this equation, okay, at 25 degrees Celsius. That's the natural log form, and we're going to go with the log base 10 form, log form. So this finally is what you see on your test. It's the Nernst equation at 25 degrees Celsius. N is the number of moles of electrons. E naught is your normal cell potential at standard conditions. So this actually is what we were talking about yesterday in lab. Okay, that's your standard potential. Okay, and you get that from, just as we talked about, basically adding up your half reactions of your reduction and your oxidation. Okay, N is the number of moles, and Q takes into consideration the non-standard molarity. Remember, at standard conditions, your molar concentration is 1.0. Okay. So that's the form we'll be using. So just to kind of remind you, this would be kind of a review thing. With regard to cell potentials, whether it's standard or not standard, if the cell potential is positive, it's spontaneous. If the cell potential is equal to 0, it's at equilibrium. If your cell potential is negative, then the reaction is non-spontaneous as written. So let's focus on that middle one. If the cell potential is equal to 0, then it's at equilibrium. And one of the things we know at equilibrium is that your snapshot, your reaction quotient Q, that's equal to K, your equilibrium constant. Okay? So if we revisit the Nernst equation, this is what the Nernst equation looks like. And at equilibrium, we'll go ahead and put a 0 in there for your cell potential. Kind of do some rearranging. Okay. And though this didn't make it, you guys have a sheet. You guys can put this on your sheet if you wanted to. I'm not sure if it'll help you for Monday or not. But at equilibrium, at 25 degrees Celsius, standard temperature, but not standard temperature, the log of your equilibrium constant K is equal to n, the number of moles of electrons involved in your redox reaction, times the standard cell potential divided by 0.0592. We're going to do an example here, and we're going to basically get to the equilibrium constant K. All right, so one last problem. And actually, this is a revisit of something we looked at just yesterday. So what if you have the chemistry is between silver and copper, okay? You would want to look at your options to see which one would be a better oxidizer and which one is a better reducer. 3 questions we're going to answer with regard to this cell. And actually the first 2 questions, the difference between these 2 questions is the molar concentration of the silver and the copper 2 ion. So in one scenario, the silver and the copper 2 are both 0.1 molar. And in the second scenario, it's reduced quite a bit. It's 0.001 molar for each of them. So we're going to use the Nernst equation. We're going to use this Nernst equation to come up with the E, the cell potential, for those non-standard conditions. The third question we're going to answer is to use that relationship at equilibrium between K and E, or E naught. Okay, so we're going to come up with the equilibrium constant. So here we go. Nernst equation coming up. So this is one of the things we looked at yesterday. We said that if you are going to do some chemical cell, electrochemical cell between copper and silver, you better go ahead and make your silver the reduction half and your copper the oxidation half. That will give you a positive cell potential. So in our Nernst equation, that's going to be your E naught. That's the standard cell potential standard conditions. All right. So in the first scenario, the molar concentration of the silver and the copper 2 were both 0.1 molar. There's your Nernst equation. The cell potential is equal to the standard cell potential, previous slide. So minus 0.0592 over N. N here is going to be 2 moles of electrons, excuse me. Log base 10 of Q. Now, here's where we get to kind of mix our units a little bit. Q is a snapshot of the equilibrium. So basically, up there in that, I'll just kind of do it this way. Up there in your redox reaction, okay, if I were to ask you to write an equilibrium constant expression for this, just ignore the fact that there's only a one-way arrow. You would write it something like this. K is equal to the molar concentration of the products raised to their stoichiometric coefficients, but anything that is a solid does not appear in our equilibrium constant expression. So it is the copper 2 plus, okay, divided by the molar concentration of the reactants, forget copper solid, raised to their stoichiometric coefficients. So the equilibrium constant expression looks like this for this cell. It's a really common mistake to kind of blow off the whole silver squared. But the reason is because the coefficient in front of the Ag plus is 2. So that's where that came from. It's going to be the same for both molar concentrations. So now we can go ahead and plug in 0.1 molar for both of these. Okay, so Q is equal to 0.1 molar divided by 0.1 squared. That's where that all came from. And that's going to be our Q in our Nernst equation. So that doesn't look too hard. So you end up with 10. 2 significant figures is your snapshot, your reaction quotient. All right, so we have everything we need to plug in. So the Nernst equation looks like this, where E, the non-standard conditions, is equal to the standard cell potential, 0.460, minus 0.0592 divided by 2 moles of electrons. That last term needs to be times the log base 10 of 10, which is 1, right? Okay, just checking. All right. So you should get 0.430, and units of cell potentials, of course, are volts. And it should make sense that it will be a little less than standard. So it's 0.460 if it was 1 molar in both the silver ion and the copper 2 plus, but it's 0.430 with those lower concentrations. So that's how that works. So let's do the other one. Okay. Oh, okay. Because I thought they were 0.001 molar in both, but it must have been 0.001 molar. Yep, yeah, I said it wrong. So this is the conditions for 2. So that's the only thing that's different is this, okay? So now instead of the silver ion also being 0.10 molar, it's 0.0010 molar. And of course, remember, we're going to square that because the coefficient in front of silver is 2, and that's how we write equilibrium constant expressions. So that's how we write Q expressions also. Of course, this is, if you do the math here, you'll get 1.0 times 10 to the 5th. That's your Q. And we're going to plug that into the Nernst equation. So our Nernst equation at this molar concentration, these molar concentrations, is still 0.460, that's your standard cell potential, minus 0.0592 divided by 2, that's the same, times log base 10. Times log base 10 of 1.0 times 10 to the 5th. So let's see what this one looks like. Drum roll, please. So it's lower yet. The cell potential is even less, which makes sense. Okay, so this is how you do that. This is how you do that. Non-standard conditions. Non-standard in this case being the molar concentration. But these Nernst equations, I just think that's weird. I was thinking about that in my office. Like, so non-standard conditions except for 25 degrees Celsius, right? So this is just going to monkey with the molar concentration. Okay. Oh, yeah, one other. This is question 3. So for the third question, we're going to use this relationship, which, again, you can put it on your note card if you want. I don't know. Or your sheet. So we were supposed to come up with the equilibrium constant K. So plugging in stuff being the standard cell potential, so log of K is equal to 2 moles of electrons times the standard cell potential, 0.460, divided by 0.0592. If you resolve what's over there on the right, you get log of K. Log base 10 of K is equal to 15.5. And so this little trick is something we kind of we've done a few times in chemistry, where if you're after this, okay, what I can do is take 10 raised to this power is equal to 10 raised to this power. And the beauty of this one over here is if you take 10 raised to the log of something, it is that something. So the cool thing about this is going to be k is equal to 10 raised to the 15.5. And on your calculator, if you take 10 raised to the 15.5, you get something in scientific notation that is raised to the 15th power. So 3.47 times 10 to the 15th. So a big K means it favors the products. Yeah. So definitely spontaneous. All right, so as has been a kind of our pattern here, these will be worth 10 extra credit points. Some of them really aren't bad. And you could do a couple of them and get 5 extra credit points if you wanted to. They'll be due when you come to take your test. And I don't have any hints, but I did go ahead and take a snapshot of them. And we can make hints up as we go if we want. So this is the first one. Write the equilibrium constant expression. So that's the K. So it's the products raised to their stoichiometric coefficients divided by the reactants raised to their stoichiometric coefficients. So let's see if we can do the first one. So K, equilibrium constant expression, right? Oh, and determine the value of K. Oh, drat. So K is equal to, looks like the molar concentration of the V2 plus squared times the molar concentration of the nickel 2, right, raised to the first power, divided by the molar concentration of the V3 plus squared. And then to come up with the K, I guess it is a little involved. So to come up with the K, you're going to have to use, and this is the one that I said I'd write on my sheet. I'm going to use that last one that we used.
This one?
Yeah. Yep, you're going to use the log base 10 of K is equal to, bless you, N E naught over 0.0592. And see, these aren't as easy as I thought they were when I was glancing at my desk, because to get your standard cell potential, you're going to have to kind of do what you're doing for your other homework that's due on Monday. Okay? But it would be good. But the next one looks like this. Just one. Voltaic cell represented by this, and it gives the cell potential. That's not the standard cell potential. There's no naught there, okay? So the Nernst equation was used to get the 1.250 volts. And you're supposed to say, what is the silver ion concentration? Did anybody do these? Should we look at these? Okay. Okay. All right. So let's think through this. To me, what I would have to do is to basically kind of, it's almost like deconstructing from that what your the redox reaction is. So to me, it's got zinc, okay, reacting with silver, okay, to form, oops, the zinc cation plus silver solid. Oops, yes, okay. So that's kind of what we have going on. It looks like it is balanced for, how do we say, balanced for mass but not for charge right now. Okay, So it looks like as zinc goes to form, how do I say this? Yep, zinc goes to form, zinc solid goes to form zinc plus 2 cation. It releases 2 electrons. You buy that? And as silver, we need to actually have 2 silver because they are going to take 2 electrons like that, and you end up with 2 silvers. Does that make sense? 0 oxidation state over there. So I'm going to go revisit this, and I'm going to do this. So far, does that work for everybody? Okay. So, if I want to write the Q in the Nernst equation from that, it's looking like this. Q is equal to the molar concentration of the zinc divided by the molar concentration of the silver ion squared. See where that all came from? Me too. So now I think we're finally ready to, almost ready. We would need to go and come up with the cell potentials, standard cell potentials for these. And be careful. It looks like you're going to go with the reduction for the silver. So you need to look these up. And you're going to have to go with the oxidation for the zinc. Right? So this one you're going to have to take times minus 1. Add those together and you'll get the E naught for the cell. Okay, that will be the cell potential. Now I think we're ready to go and look at the Nernst equation. According to the Nernst equation, okay, E is equal to E naught, which is over here, minus 0.0592 divided by N, and N is 2, times log of Q. And we said actually this is Q. And if we look at what we know, the molar concentration of the zinc was given as 1 molar. And the only thing you don't know is the molar concentration of your silver ion. Oh, I should say too, the E, do you guys buy this? That the E of the cell actually was given as 1.250. .250. So you know this from that, you know this from this, and the only thing you don't know is the silver ion. Okay. This one, use the Nernst equation to calculate the cell potentials at non-standard conditions, 25 degrees Celsius though, for these things. Let's just look at A. To me then, you'd have to do kind of what we just did. I would kind of read from left to right, and I would pull out the redox reaction for A. Okay, and you're going to have to come up with the standard cell potential because you're using the Nernst equation, and the molar concentrations are given here. So in this case, the thing you're solving for is this. Okay, because you get this from doing the work up front, kind of like we did before. See, that's the reason I think you have to do what we just did, is you need to come up with a number of moles of electrons, and you have to do that work we did. Log base 10 of Q. And of course, in order to know what Q looks like, you have to know what sort of reaction the redox reaction looks like. So those are, okay, so, what's that?
There's one
You're a pain in the butt. Yeah. Okay, so here we go. If you really are serious about getting extra credit, if you just do A here, that would be great.
Okay, so
Just A, don't worry about B.
okay.
Let's see what else we got. Oh, and if you're, I should stop saying that. And if for extra credit, I say if you're serious, for extra credit, if you just do, I did A, but if you follow my pattern and do B here for 26, you don't have to do A and C. Just follow my pattern that I laid out for A and do it for B.
Okay.
So just do B there for extra credit. This is looking better. That one. And one there. Oops. Was that it? I guess that was it. Is that the last one that was listed?
No, there's 38.
Just one more? Okay. So that one looks like... Oh, not that one. Not that one. Okay, this one. So let's just do one of these for extra credit too. So you do A. Do A for extra credit there. So use the Nernst equation to calculate. So that's that's similar to 37. Okay? Any questions? Okay. So, woohoo! We are officially done.